move on from descriptive statistics into inferential statistics. We're going to try and make, descriptive statistics is stuff like means and standard deviations, describing your data. But if you want to go beyond your data and say, well, I think that, more than 27% of people write with their left hand, or that, the average IQ of students in my stat class is at least 110. Those kind of things go beyond your data, and you're trying to make an inference. Now, one big difference between a math class and a stat class is that in a math class, you prove things. In a stat class, we're like, we're pretty sure. We're 95% confident, but we can never actually prove things in a stat class, Vlad. So let's talk about hypothesis tests for a population proportion. Now, what I've got here is kind of a generically framed hypothesis test, and we're going to be doing the same thing for population proportions that we're going to do for population means. We're going to take a look at some assumptions that need to be in place in order to do your hypothesis test. You're going to start out by stating your null and alternative hypothesis, decide on the significance level, and then input the data. Now this second part, find the critical values, I've kind of done away with that for you. And that's because we're going to use StatDisk. You're going to have to determine a p-value, decide to reject or fail to reject, and then state your conclusion in words. So let's look at how that plays out. It's going to be the same kind of 6 steps regardless of what hypothesis test you're working with. Now, as far as the assumptions are concerned, let's try and be somewhat careful in checking these things. So our assumptions include that the observations come from a simple random sample. That's going to be beyond our capability to control. The ones that we want to worry about are the conditions for a binomial distribution are satisfied. All right, so going back here a little ways. What has to be true for something to have a binomial distribution? Do you remember how to check it?
Fits.
Yeah, if it fits. Well done, Marvin. What does all that stand for? Does anyone remember? Fixed number of trials.
Yeah, that part. Independent.
Independent. Two possibilities.
And same something, yeah. Same probability of success. Same possibility of success.
Same probability of success throughout the trials.
Now I know it. I couldn't remember. Right?
Extra credit. Okay. So those are your conditions for something to be a binomial distribution. Now just a little bit more of a reminder, your probability of success in a binomial trial is P. What's the probability of failure? It's 1 minus P, or sometimes we call that Q. So there's your probability of failure. And what this last condition is basically saying you expect more than 5 successes and 5 failures. Now I'll give you some stuff while you're writing all that down. Essentially what this means is that the normal distribution is a good approximation to the binomial distribution in this circumstance. So more information than you need. Let's work through one of these where we state all these. Null and alternative hypothesis. Significance level. Alpha is typically going to be 0.01 or 0.05. Now the book in my stat lab will use some other things like 0.1. I don't think anyone in any serious capacity is going to use a level of alpha that big, but you never know. Now rather than do this one as is, let's do it kind of like a hypothesis test for, let's see. We need an inhaler drug. Would it be like albuterol?
Yeah, that works.
Albuterol. All right, so albuterol. Albuterol is used to treat asthma. In a clinical trial, 15 of 253 treated subjects experienced headaches based on data from the manufacturer. The accompanying calculator display shows the results from the test, blah, blah, blah. All right. What I want to focus in on is this part right here, where we've got blah, 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 B-L-A-H, B-L-A-H, repeat ad nauseum. All right. This part here, and we also want to pay attention to some of the data. Now let's just take a rough pass through and see if this fits. Is it binomial data? Well, is there a fixed number of trials? How many would that be? 253. How many of those were, for lack of a better word in this case, successes? 15. Now they tell us to use alpha as 0.01. Okay. But is this a binomial random experiment? Well, do we have a fixed number of trials? Yes. Are they independent? If somebody experiences a headache on albuterol, is that going to influence somebody else experiencing headache on albuterol? No. So they're independent. There's two possibilities. Either you got a headache or you didn't. And that probability of success is going to stay the same throughout the trial. It's not going to change all of a sudden based on any other circumstances, so we're good on that one. Let's run through our steps here. We want to test the claim that less than 9% of treated subjects experience headaches. So let me highlight that. Let's see. Less than 9% subjects experience headaches. Okay. So that's our original claim. So I'm going to write that as OC, our original claim. What parameter am I testing? Keep in mind that you have several different choices for parameters, mu, sigma, or p. You shouldn't be writing anything else in your null hypothesis. So,
Me? No, you're right.
Is this talking about a mean? 15 out of 253 people, is that about a mean?
No.
Is it about a standard deviation?
No.
Is it about a proportion?
No. Yeah. My bad. I got it groove.
Got in a groove, yeah. So it's about a proportion. So that's going to be the parameter here. And that parameter is going to be p is less than 0.09. Evan, should that be in the null or alternative hypothesis? Awesome. The alternative hypothesis. So safe. If p is less than 0.09 is in the alternative hypothesis, what should I put in the null hypothesis? All right, p is greater than 0.09. Somebody put the a on the plus on that a for us. What else do I need there? Greater than or equal to. And as a reminder here, my stat lab is going to do a little different, right? What's my stat lab going to put here? It's just going to put the equals. It's not going to put the greater than or equal to. I don't know. I just do this because I think it makes it a little bit more easy, a little bit more user-friendly. Step 2, decide on the significance level. That should be given to you by the problem. In our case, significance level is alpha is 0.01. Step 3, input the data. All right, where do you think I should input the data? Where would it make sense to input the data? StatDisk, yeah, StatDisk. So let's go to StatDisk. StatDisk rocks. StatDisk, I can't tell you how much easier your life is with StatDisk. Now, 99% of the time with StatDisk, you're going to want to either go to data or analysis. And really 99% of that, you're going to want to go to analysis. Does it look like there's anything here that might be helpful? No. Up and down, not left and right. Amy, what do you got? That's not a bad choice, but it's not really where we're going with this one. Hypothesis testing. We're testing a hypothesis about a proportion with one sample. Okay. Now to do this, you're going to have to set up the alternative hypothesis. It's going to want to know what you got going here. So, in our case, do I want a left tail, right tail, or two tail alternative? Left tail. So which one of these looks correct? 1, 2, or 3 here? Vlad, which one are you liking? Second one? All right. We agree with that? Second one?
Don't listen to me.
You thought it was the third one? All right. Does someone want to cast a deciding vote?
It's
First
two.
one, second one, or third one?
Glad on that one.
Third one.
Oh, now y'all want to speak.
This should be a left tail. P is less than something. So that was the third one.
Oh.
Our significance level. What was our significance level for this particular problem?
0.01.
0.01. Claimed proportion. Now that claimed proportion comes from your alternative hypothesis. So this is your claimed proportion. Not your alternative, your null hypothesis. That's your claimed proportion. So that's the number you're going to fill in for this blank. 0.09. What was our sample size? 253. And how many successes did we have out of those? 215. No, 15.
No,
15.
15.
15. Who said 215?
You.
Shh. Don't gaslight me on TV. All right. 215 and bam. All right, so we got the first 3 steps. Let's take a look at the 4th step. We input our data. What's the 4th step? Find the p-value. Well, what's the p-value?
The p-value is 0.0878.
I think that was half of that, really.
Wait, where did y'all get that? What did I do?
Right here.
That's not what I got.
Well, there's a problem someplace between the computer and the chair.
I know he was about to say that. That's not what I got.
All right. Let's take a look here. P-value is 0.04392. All right. P equals 0.04392. Step 5. This is your money step.
Wait, so is
Joyce, question?
No. Wait, what is Z? Can you go back to Z real quick? What's Z?
I don't have a Z. There's a P.
Z equals what's in that?
Where?
Part B. Part B. Yeah.
Which one are you worried about?
Part B.
Part B?
Yeah.
We're not doing this.
Okay. Oh.
We're just doing our own thing. We're veering off into uncharted waters. So we're doing
bring me back?
then don't learn while it's cold out. All right. So the next step here, we're following along this chart. The next step is to determine if the test statistic falls in the rejection region, or if you're using the p-value approach, which we are, or is p less than alpha. In fact, I get that right here. If p is less than alpha, then reject H naught. So are you going to reject H naught in this case or no?
Yes.
Yeah. 0.04392 is less than 0.05, therefore reject H naught. Oh, is it 0.01? Oh, that's right. That's right. Yeah, I'm sorry. And I get in a little groove here because P is... No, Christine is right. P is... The alpha is 0.01.
So it's greater than. So we're not going to reject.
Failed to reject. There we go. This should be a 0.01. This is not true. This is bigger than that, so you fail to reject. And I need to post this little bit here on D2L for us because I forgot to print it off today. But let's see, where is it? Yeah, right here. We're going to be very particular about how we state our conclusions. So this is going to be a little chart that I'll give to you to help you state your conclusions. So let's take a look at where we were for this one.
So
Does-
because we failed to reject.
Well, we got to start before that. Here's your original claim. All right, folks, if you have some questions, please direct them to me. Joyce, Rael, if you could. Thank you. There's your original claim. Let's take a look at our little flow chart and decide where we're going to go. Does our original claim contain the possibility of equality?
No.
No. So, all right, so that's a no. So that means we branch down here. Did we reject H naught, or did we fail to reject H naught?
No.
Fail to reject H naught. So the way we're going to state our conclusion then is that there's not sufficient sample evidence to support the claim that, and then you have to state the original claim in words. Now, when you state these things, when you write out your conclusion in words, please don't use parameters. I don't want to see the symbols of mu or sigma or p. You shouldn't talk about null hypothesis and alternative hypothesis. It should just be a nice conclusion written in words that somebody could read and understand. So you're given half of it. All you have to do is write this original claim in words. And that original claim in words is actually given to you in the problem. So let's just keep it as easy as it should be. There is not sufficient sample evidence to support the claim that. So we'll start out with that. I mean, that much is given to you. So 6, there is not sufficient sample evidence to support the claim that. And now you get to state your original claim in words. So that's going to come back up to here, that less than 9% of treated subjects experience nausea or experience headaches. So let's finish it off that less than 9% of treated subjects experience headaches. There you go. That's your conclusion in words. So we've done, all 6 parts of this type of problem. I want to do one last example like this, just for giggles, and then we'll call it a day. You don't know about that? Are we okay with our conclusion, the way we wrote that down? I will post that sheet on D2L, and I'll give you a copy of that sheet to use on your exams. So that's about as generous as I think I can be. Yes, Safe?
Do we not need to include fail to reject in the conclusion?
No. It's a good question. No, we don't need to include fail or reject, because basically the conclusion is saying we can't reject this because there's not enough evidence. We can't get to this. We can't support this because there's not enough evidence to reject that. So it's kind of in there. There's a lot of different ways we could word it, but I'm trying to give you like a cookie cutter approach that you can just fit these things in and do them without too much stress and too much worry there. All right. last but not least, let's go to, let's see. Yeah, this one. Let's back this up a little bit. I hope the audio comes through on this when we do the recording.
Too accurate for sand people. Only Imperial stormtroopers are so precise.
Now this was something I actually saw in the theaters when I was really young, and I remember that scene. I was like, oh, that was so cool. How accurate are stormtroopers? Well, not as good as they claim. Yeah. Let's take a quick peek at it. That's not looking too good. That's looking like 1 in 10 so far. And it just keeps on getting worse. So, all right, good enough. Now I got some summary numbers here for us. So the summary numbers in the series total are 43 hits out of 1,411 shots. Now, I'm not going to go through all the assumptions here, but let's just throw it out there that, I don't know, my claim is that the stormtroopers hit less than 1 in 20 shots. So that's less than 5%. So the claim is that stormtroopers hit less than 1 in 20 shots. Stormtroopers hit less than 1 in 20 shots. And that's going to be 5%. So that's our original claim. Let's see if we can't turn that into a hypothesis. So my original claim in terms of original claim is going to be that P is less than 0.05. Now, quite often, you're going to set your value of alpha. It's going to be a C, original claim. You're going to set your value of alpha up depending on, how critical it is that you not make a type 1 error. In this case, we'll set our standard pretty high. We don't want to get this wrong. Not that there's really any consequence to it. We'll set alpha equal to 0.01. Here's your original claim. MA, do you think that should be part of the null or alternative hypothesis? Yeah, it should be part of the alternative. And Mason, if this is part of the alternative, P is less than 0.05, what should I put in here as the null? Awesome, thank you both. Greater than or equal to. So there's your first step. Your second step, we've already taken care of. We decided that alpha is going to be 0.01. The third step is to input the data. All right, so let's do that. And the data that I want to input is this stuff down here, our series totals. So let's put that into StatDisk. Significance level, 0.01. Claimed proportion. What should I put for the claimed proportion? Where's that coming from?
The accuracy. Oh wait,
So
no,
the
the claim proportion you said is your null hypothesis.
There's your claimed proportion. Well done. So your claimed proportion, that's always going to be found in the null hypothesis. So the claimed proportion in this one is 5%. Is it going to be a left tail, right tail, or two tail test? Royale, what do you think? Two tail? Joyce, is she right? Maybe. All right. So, someone want to cast a deciding vote? So going back to section 8.1 material, remember this sign points in the direction of the tail. So this is going to be a right tail test. We're going to be finding p-values, or at least StatDist will find a p-value by the area in the right tail. If it points to the left, well, then you get a left tail test. So this is going to be a right tail test. But the reason that you have to be careful about this and pay attention to it is because they're going to ask you to fill this in. You've got 3 possibilities here. Which one looks good? 1, 2, or 3? 3. So our population proportion is less than the claim proportion. Claim proportion is going to be 0.05. Our sample size was 1,411. And of those, these really accurate stormtroopers got a total of 43 shots. Yeah, it's not so good. It's about a 3% hit rate. All right, what information do I need here? So we're now on to the 4th step. What information is being asked for in the 4th step? P-value. So the p-value. P-value is 0.00038. And so Liv, once again, you got P's doing a couple different things, right? You got a P from our null hypothesis, which is the population proportion of hits. And you got your p-value, which is a probability, and that probability, we want to see, is it less than our alpha? So that's going to be our step 5. Is our p-value less than alpha? Is this smaller than 0.01? Yes, it is. So does that mean we reject or fail to reject? Which one are we doing in this one? Anyone got that? Got a couple people for reject. Derek, do you agree? Reject or fail to reject? Okay. So going back here, if the p-value is low, reject. If the p-value is greater than alpha, then you're going to fail to reject. So reject H naught. Let's look at wording our conclusion. Because I'm having StatDist do a lot of work here for you, I'm going to ask that you be pretty careful with your conclusions. You'll have this available to yourself. Let's see if we can't follow the right branches down this tree to figure out where we're going to set up our conclusion. Does the original claim contain the condition of equality? So let's go back here. That was our original claim, less than 5%. Doesn't contain the condition of equality, so we'll branch down. Did we reject H naught? Yes. So we're going to go to the right. The sample data support the claim that. So we'll start out that way. The sample data support the claim that. And then you just want to state what the claim was. Stormtroopers hit less than 5% of their shots. Yay. And that's it. That's it.
That's it. Just 6 steps.
That's it. 6 steps. Now the nice thing about the way I set this up is that we're going to be doing the same kind of 6 steps for lots of different tests. So it's going to give you a chance to get really used to this and really into a rhythm with all these different hypothesis tests. Maybe we'll do our testing of some M&Ms later on. All right. Have yourself a great day and see you.